Every account of Sudbury's transformation opens with the same tidy image. A blackened, moon-like wasteland, so thoroughly ruined by mining that NASA itself sent astronauts there to train for the lunar surface before the city miraculously regreened itself into the forested landscape visitors find today. That's the postcard version, and the twist inside it is the part almost nobody gets right. The astronauts didn't come to Sudbury because it looked like the moon. They came because a meteorite, roughly 1.8 billion years ago, had built something underneath this city that genuinely resembled lunar geology at the molecular level. And the fact that the ground above that geology also happened to look like a bombed-out wasteland was, for NASA's actual purposes, close to irrelevant. I went looking for the moment Sudbury's ruined landscape became useful to space science. I found a myth that had almost nothing to do with why the astronauts actually came, layered on top of a genuinely staggering, self-inflicted environmental catastrophe that the myth has spent 50 years quietly overshadowing. It's worth sitting briefly with how strange it actually is that both halves of this story are true simultaneously, and neither one causes the other. This is not a case of a city spinning a flattering story to disguise an ugly one, the way so many of these Canadian founding myths tend to work. It's closer to the opposite. A genuinely remarkable scientific fact. A nearly 2 billion-year-old impact crater, significant enough to draw the American space program north of the border, got quietly overwritten by a considerably less accurate, but more visually intuitive explanation. One that happened to align with an entirely separate and entirely real environmental catastrophe unfolding on the same ground at almost exactly the same time. Two true stories collided, and the wrong one won the retelling. Chapter 1. A rusty rock. A blacksmith almost ignored. Start with the accident, because Sudbury's entire economic and environmental history traces back to a single moment nobody involved was looking for. In August of 1883, construction crews were blasting a rock cut for the new Canadian Pacific Railway line through the rugged terrain of northeastern Ontario, in a stretch of country nobody at the time considered economically significant. Thomas Flanagan, a blacksmith working on the crew, noticed a rust-colored patch of exposed rock in the freshly blasted cut, a color distinctive enough to catch his attention amid the ordinary grey stone the crews were used to seeing. Flanagan and others took samples, which were analyzed and found to contain copper-nickel sulfide, the surface signature of an ore body that would, over the following century and beyond, make this stretch of the Canadian Shield one of the richest metal mining districts on the entire planet. Here's what doesn't add up if you assume this was a straightforward, well-understood discovery from the start. The land around the find was purchased almost immediately by 4 men, brothers William and Thomas Murray, along with Henry Abbott and John Lawfrin, for roughly $1 an acre, the standard going rate for mining concessions at the time, a price that reflects how little anyone involved actually understood about what sat beneath that ground. Nickel itself had almost no significant industrial market in 1883. It would take developments in steel alloys through the following decade, and specifically the demand created by nickel-steel armor plating for naval and military applications through the 1890s, before this metal became genuinely valuable rather than a geological curiosity. Entrepreneur Samuel J. Ritchie founded the Canadian Copper Company at Coppercliff in 1886, initially chasing the copper in the ore rather than the nickel, and it took years of further metallurgical development before the industry understood it was sitting on something considerably more significant than a modest copper deposit. Worth noting, too, that this wasn't even the first time the significance of this ground had been flagged and ignored. Provincial surveyors had reportedly noted geological anomalies in the district decades before Flanagan's discovery, filing reports that raised no particular interest at the time. In a young dominion, Confederation itself had only occurred in 1867, where the mining industry barely existed as an organized economic sector at all, and where almost nobody in a position of capital or authority had the specialized knowledge to recognize what those anomalies actually represented. The eventual, celebrated 1883 discovery was, in that light, less a first identification of the district's mineral wealth than a fortuitous, accidental rediscovery of something the historical record had already brushed past once already, simply because the country wasn't yet equipped to notice it. So what was this ore body actually made of, geologically speaking? And why would that specific composition matter to an American space agency nearly a century later? The answer to that question is the single fact this entire story pivots around. And it starts not in 1883, but nearly 2 billion years earlier, in an event considerably more violent than a railway blasting crew. It's worth pausing on how quickly the settlement around this discovery grew, because the pace itself tells you something about the region's transformation from empty bush to industrial hub. The site received its name from CPR construction superintendent James Worthington, who named the new railway station after his wife's hometown in England, a nod to distant domesticity that had almost nothing to do with the industrial reality about to grow up around it. Within a few short years of Flanagan's discovery, prospectors including Thomas Froude, Francis Crean, Henry Totten, and James Stobie had all staked claims across the surrounding district, each eventually giving his name to a mine, and a community began forming that drew Anglophone settlers, a substantial French-Canadian population, and waves of immigrant labor from across Europe, all converging on a stretch of the Canadian Shield that, a decade earlier, had registered on almost nobody's map as economically significant at all. Leave a like, subscribe if you want more of these, and tell me in the comments which Canadian city's founding myth you think deserves this same kind of digging. Chapter 2. Burning the ore in the open air. The geological explanation didn't arrive for decades. What arrived immediately once the Canadian Copper Company and its rivals began actual industrial-scale extraction was a processing method that would define and devastate this landscape for the next 4 decades. Separating nickel and copper from the surrounding rock required removing sulfur from the ore before it could be smelted into usable metal. And the method the industry adopted, beginning with the first roast yard and smelter established at Coppercliff in 1888, was about as crude as 19th-century industrial chemistry allowed. Crushed ore was piled onto massive open-air beds of cordwood, sometimes stacked many meters deep, and the wood was set alight beneath it. The fire burned for weeks at a time, driving off sulfur as it went, directly into the open air, at ground level, with no capture technology of any kind, releasing dense clouds of sulfur dioxide that spread across the surrounding countryside as ordinary, uncontained smoke. Here's the detail that turns this from a simple story of primitive industrial technology into something considerably more deliberately destructive. Between 1913 and 1916 alone, the Mond Nickel Company stripped essentially all standing vegetation from the area around Coniston, specifically to supply cordwood fuel for its own roasting beds, meaning the forest wasn't simply an incidental casualty of the smelting process. It was consumed directly as raw material, cut down deliberately to feed the very fires that were simultaneously poisoning whatever vegetation the logging itself hadn't already destroyed. The roasting method remained the industry's primary means of separating minerals until 1929, meaning this specific, doubly destructive practice, burn the forest to fuel the fire, let the fire's fumes kill whatever forest the fire didn't already reach, ran continuously for roughly 4 decades. So how much sulfur dioxide did 4 decades of open-bed roasting actually release into this landscape? And what did that volume of continuous, ground-level acidic smoke actually do to the ground beneath it? The cumulative figure, once historians and scientists finally tallied it, is large enough to make the astronauts' later visit look, by comparison, like a footnote to a considerably larger and more sustained catastrophe. It's worth being specific about the sheer physical scale these roast beds reached, because open-air fire understates how industrially massive the operations actually were. Some roasting beds were stacked many meters deep with crushed ore and cordwood together, covering areas the size of several city blocks, and burned continuously, not for hours or days, but for weeks at a stretch, with new fuel and ore added as older material finished roasting. Records from the period describe roughly 11,000 loggers working the surrounding forests by the late 1880s alone, feeding an industrial fire-based chemistry process that had no equivalent anywhere else in Canada at this scale, and few equivalents anywhere else in the industrializing world. The visual and physical experience of living near one of these operations, by contemporary accounts, meant near constant exposure to acrid, sulfurous smoke at ground level. Not an occasional industrial accident, but the ordinary daily condition of the surrounding communities for the better part of 2 generations. Chapter 3. 40 Years of Open Fire. Across the roughly 40 years the open roast yard method remained in use, historians and environmental scientists studying the district have calculated that the practice released approximately 100 million tons of sulfur dioxide gas into the atmosphere above Sudbury, a cumulative figure large enough that its consequences are still being measured and, in places, still being actively reversed more than a century later. The physical transformation this produced is worth stating in specific numbers rather than general description, because the scale is genuinely difficult to picture in the abstract. By the point the damage reached its worst extent, an estimated 20,000 hectares of land around the city had become completely barren, no vegetation growing at all, with a further 80,000 hectares reduced to semi-barren condition, and roughly 7,000 lakes across an area of some 17,000 square kilometers acidified badly enough to damage or destroy the aquatic life they had previously supported. Later, broader estimates of the total affected landscape run as high as 250,000 acres, either completely or nearly barren, an area regularly compared, by observers at the time and since, to the surface of Mars, rather than any landscape recognizably belonging to the temperate forests of northeastern Ontario. Exposed rock across large sections of the district turned visibly black, both from direct chemical staining and from the simple absence of any soil or vegetation left to cover it. Here's what's worth holding on to about this specific mechanism of destruction, because it distinguishes Sudbury's landscape from most other heavily polluted industrial sites of this era. This wasn't primarily a story of toxic waste buried underground or contaminated water leaching slowly through soil. It was continuous, decades-long ground-level acid smoke released directly at the height a person breathes and a plant grows, blanketing an already thin layer of Canadian shield soil that had never been especially deep or fertile to begin with. Once that thin soil layer eroded away under decades of acidification, with nothing left to hold it in place once the vegetation it supported had died, the underlying Precambrian bedrock was left essentially bare, exposed in a way that would have taken the same landscape many thousands of years to expose through purely natural erosion. So by the time this specific, self-inflicted process had run its full course, what kind of landscape had Sudbury actually produced? One merely damaged by industry, or one that had been chemically and physically stripped down to something closer to raw planetary bedrock? The historical photographs and scientific surveys from the mid-20th century both point toward the second description, and that description is exactly what would eventually draw an entirely unexpected category of visitor to this specific stretch of northern Ontario. Before moving on to that visitor, it's worth briefly establishing the geological origin that made this specific ore body possible, since it becomes directly relevant later in this account. Approximately 1.8 billion years ago, A massive meteorite, moving by later scientific estimate at speeds in the range of Mach 100, struck the Earth at this exact location, releasing energy equivalent to several billion tons of TNT, an impact violent enough to melt and fracture bedrock across an enormous surrounding area, and to concentrate nickel, copper, platinum group metals, and gold into the resulting impact structure in unusually rich, accessible concentrations. This was not, in other words, an ordinary sedimentary or volcanic ore deposit of the kind found in most mining districts.
It was the geological signature of a genuine cosmic collision, preserved essentially intact for nearly 2 billion years, sitting directly beneath the same ground that decades of roast-yard fires had scoured bare. The ore that built Sudbury's fortune and the ore that would eventually draw astronauts here were, quite literally, the exact same rock, examined for two entirely different reasons a century apart. Chapter 4. The tallest chimney in the world. By the 1960s, growing provincial regulatory pressure and mounting public concern over air quality had made continued ground-level sulfur dioxide emissions at anything close to historical levels politically and legally unsustainable, and the mining industry, led by the International Nickel Company, INCO, formed through the 1928 amalgamation with Mond Nickel, began investing seriously in emissions control for the first time in the district's history. The most visible product of that investment, completed in 1972, was the INCO Superstack. At 381 meters tall, it became, at the time of its construction, the tallest freestanding chimney in the world, and it remains today the second tallest freestanding structure in Canada. Its engineering logic was, worth being honest about, considerably simpler than it might sound. Rather than capturing and neutralizing sulfur dioxide before release, the Superstack was designed primarily to disperse the same volume of pollutant much higher into the atmosphere, where prevailing winds would scatter it across a far wider geographic area before it settled back to ground level, solving Sudbury's specific, concentrated local air quality problems substantially by exporting a diluted version of the same pollution considerably further afield. That solution was, in fact, controversial even at the time, and not only within Canada. Sudbury had, at points, been recorded as the single largest source of sulfur dioxide emissions anywhere in the world, and once that pollution began traveling further via the Superstack's height, American authorities across the border raised specific, formal objections to Canadian sulfur dioxide drifting into United States airspace and contributing to acid rain damage well beyond Ontario's own borders. An early, concrete instance of the transboundary acid rain disputes that would come to define much of North American environmental diplomacy through the 1970s and 1980s. So did building the tallest chimney in the world actually solve Sudbury's underlying pollution problem, or did it simply relocate the same volume of poison somewhere less immediately visible? The honest answer sits somewhere in between. Local, ground-level sulfur dioxide concentrations genuinely did fall substantially once the Superstack came online, reducing the acute, immediate fumigation events that had made the area around the smelters nearly uninhabitable for vegetation at close range. But the Superstack alone did not stop emissions. It redistributed them, and it would take considerably more than a taller chimney, decades of further smelting technology improvements, tighter regulation, and a citizen-led restoration effort described later in this account, before Sudbury's landscape began genuinely recovering rather than simply having its damage exported over a wider radius. And it was in this exact window, in the years immediately surrounding the Superstack's construction, that the landscape it sat atop drew the attention of the United States space program. Worth noting, too, is how long it actually took regulators to force this level of investment in the first place, given how well documented the roast yard damage already was decades earlier. Provincial pollution control regulation tightened only gradually through the 1960s,
and the industry's own major capital investment in emissions infrastructure, culminating in the superstack itself, arrived nearly 40 years after the open roastbed method had already been abandoned in 1929 in favor of enclosed smelting processes that were, on their own, still releasing substantial uncontrolled sulfur dioxide throughout the intervening decades. The gap between primitive roasting method discontinued and meaningful emissions control actually implemented runs to more than 4 decades, a delay during which the surrounding landscape continued absorbing damage from enclosed smelting operations considerably more modern than open roast beds, but still, by any contemporary environmental standard, badly under-regulated. Chapter 5. The astronauts who came to study rock, not scenery. In July of 1971, Apollo 16 astronauts John Young and Charles Duke arrived in Sudbury for 3 days of geological field training, working alongside INCO's own geologists to study the district's distinctive impact crater structures ahead of their scheduled mission to the Moon's Descartes Highlands the following April. A year later, in May of 1972, the crew of Apollo 17, Commander Eugene Cernan, Command Module Pilot Ronald Evans, and Lunar Module Pilot and trained geologist Harrison Schmitt made a similar visit, ahead of what would become the final crewed lunar landing mission in December of that year. Here's the detail that the popular retelling of this story gets backward almost every single time. And it's worth stating plainly because Sudbury's own residents have spent decades correcting it. NASA did not send its astronauts to Sudbury because the blackened, barren landscape produced by a century of mining and roasting looked like the surface of the Moon. The visits happened because Sudbury sits at the edge of one of the best preserved, most scientifically significant meteorite impact structures anywhere on Earth. The Sudbury Basin, formed when a meteorite roughly 1.8 billion years ago struck the planet with a force estimated in the billions of tons of TNT equivalent, producing a crater whose geological remnants, unlike most impact sites on Earth, had survived largely intact and accessible at the surface. NASA's actual training objective was teaching its astronauts to distinguish between impact crater geology and volcanic crater geology before they encountered similar formations on the lunar surface, using shatter cones and breccia formations specific to Sudbury's impact structure as real-world reference material no volcanic landscape could have provided. Commander John Young later radioed back to mission control from the actual lunar surface, holding up a moon rock with a comment that makes the true purpose of the Sudbury visits about as explicit as it can get. "This looks like Sudbury rock." Planetary scientist Michael Dentz, who personally guided both training visits and has spent 60 years studying meteoric impact structures, has been specific and consistent in later interviews about how thoroughly the moonscape explanation misrepresents what actually happened. As he's described it, NASA in Houston decided to make Sudbury a routine part of its training program specifically because of the impact geology. Full stop. The visual state of the surrounding land at the time was, for the program's actual scientific purposes, essentially incidental. The media covering the visits, largely lacking geological training themselves, seized on the more visually striking and easily explained story instead. Astronauts training on a blackened wasteland because it resembled the desolate lunar surface they were preparing to walk on. That framing made for a cleaner headline than "Astronauts Study Impact Crater Rock Formations for Geological Reference," and it stuck so thoroughly that, more than 50 years later, it remains the version most people who've heard of Sudbury's NASA connection actually believe. So which version of this story is more remarkable? A city whose ruined landscape happened to resemble the Moon closely enough to train astronauts on? Or a city that sat, coincidentally, on top of genuinely significant lunar-relevant impact geology, while also happening to be in the middle of one of the worst self-inflicted environmental catastrophes in Canadian industrial history
at almost exactly the same moment. The second version is the one the actual scientific record supports, and it's considerably harder to compress into a single clean anecdote, which may be exactly why the simpler, incorrect version outlived it. The specific scientific problem NASA was trying to solve at Sudbury is worth spelling out in a bit more detail, because it explains precisely why an impact structure, rather than a visually barren landscape, was the actual draw. Apollo 16's planned landing site at the Descartes Highlands had originally been selected partly on the hypothesis that the region might be volcanic in origin, a hypothesis that, as Commander John Young later noted, turned out to be wrong once the crew actually reached the lunar surface. Distinguishing volcanic terrain from impact terrain in the field, using nothing but visual inspection and hand-sample geology, was a genuinely difficult skill that required real-world practice on formations scientists already understood well, and Sudbury's shatter cones and breccia, rock literally shattered and reassembled by the force of an ancient impact rather than formed by volcanic processes, offered exactly that kind of unambiguous training material. Apollo 17's Harrison Schmitt, the only professionally trained geologist to walk on the lunar surface during the entire Apollo program, was reportedly visibly excited during his own Sudbury visit, at one point carrying a large boulder down a hillside specifically because its impact-related characteristics were unlike anything he'd encountered before. The reaction of a genuine specialist encountering useful new reference material, not a tourist admiring a desolate view. Chapter 6. 10 million trees, one bag of line at a time. Whatever NASA's astronauts were actually there to study, the landscape they walked across in 1971 and 1972 was, by any measure, still recovering from decades of acid damage, and the deliberate, organized effort to reverse that damage was only just beginning around the same years. A formal Regreening Program was introduced by the city of Greater Sudbury in 1978, bringing together representatives from municipal government, academic researchers at Laurentian University, community volunteers, and, notably, the same mining companies, Inco and Falconbridge, whose historical operations had produced the damage in the first place. The technical approach the program developed was, in its basic mechanism, straightforward, even if executing it across tens of thousands of hectares of acidified bedrock took decades of sustained effort. Crushed agricultural limestone, applied at roughly 10 tons per hectare to neutralize decades of accumulated soil acidity, followed by the planting of hardy grass species selected specifically for their tolerance of the district's still difficult growing conditions. And eventually, once that initial ground cover had taken hold and begun stabilizing the soil, hardy tree species suited to reclaiming genuinely degraded land. The scale this program eventually reached is worth stating plainly, because it represents one of the largest sustained land reclamation efforts undertaken by any city anywhere in response to industrial damage it caused to itself. By 2020, 42 years into the program, volunteers and crews had planted close to 10 million trees across the Sudbury landscape, a milestone specifically delayed into 2021 by pandemic-related planting season disruptions rather than missed outright. The program has continued past that milestone in the years since, with the explicit long-term goal of restoring roughly 200,000 acres of damaged land, a target the city was, as of the early 2020s, only about halfway toward reaching, even after 4 decades of continuous work. A pace worth sitting with, since it illustrates just how much more difficult undoing this specific kind of chemical and physical land damage turns out to be than the original industrial process that caused it. So does a program this large and this sustained actually prove that Sudbury successfully reversed its own environmental catastrophe? The results, described in the next chapter, suggest the honest answer is closer to substantially, but not completely, and only because the underlying pollution itself was also brought under far tighter control at the same time. Regreening land that's still being actively poisoned doesn't work, which means this story's environmental recovery only became possible once the industrial side of the equation changed as well. The specific collaborative structure the program relied on is worth describing in a bit more detail, because it represents a genuinely unusual arrangement for an environmental restoration project of this scale. Rather than treating the mining companies as adversaries to be regulated from outside, Sudbury's Regreening Program deliberately brought Inco and Falconbridge, later Vale and Glencore, directly into the planning and funding process, alongside municipal government, university researchers, and volunteer labour, on the practical logic that the companies with the deepest institutional knowledge of the district's soil chemistry and the deepest financial resources were also the parties whose historical operations had caused the damage in the first place. That arrangement produced real friction at points over the decades. Questions about how much financial responsibility the companies should bear relative to public funding, and disagreements over which sites should be prioritized for treatment. But it also meant the program had access to industrial-scale resources and technical expertise that a purely volunteer or purely municipal effort would have struggled to match. Ecologist Peter Beckett has specifically credited this multi-stakeholder structure, sustained essentially unchanged across more than 4 decades and multiple changes in corporate ownership, as one of the key reasons the program achieved results at the scale it ultimately did. Chapter 7. What the land actually learned to do. The combination of dramatically reduced sulfur dioxide emissions, falling by industry figures from the 1990s by approximately 90% from historical peak levels, and 4 decades of deliberate liming, seeding, and tree planting produced results that scientists monitoring the district have been able to measure with genuine precision rather than relying on impressionistic before and after photography alone. Laurentian University biologist Peter Beckett, who has been involved with the regreening effort since its earliest years, has specifically tracked not just visual vegetation recovery, but the underlying ecological function that recovery represents. How much atmospheric carbon the regenerated forest cover is now actively capturing and storing, a metric considerably more scientifically meaningful than simple green coverage on a map. Small lakes that had been rendered essentially lifeless by decades of acidification began showing measurable recovery in aquatic life once sulfur dioxide levels fell far enough for pH levels in the surrounding watershed to stabilize. A recovery researchers were able to document directly by monitoring specific water bodies across the transition. By the early 2020s, Beckett and colleagues were describing certain regreened sites within the district as having reached a point where continued human intervention was no longer necessary. Locations where natural ecological succession could, for the first time in over a century, be trusted to continue on its own without further deliberate management. Here's the detail that gives this recovery its genuine significance, rather than treating it as simply a return to some prior natural state. Sudbury's air quality, once among the worst on the entire planet by sulfur dioxide volume, has been specifically credited, in later regulatory and industry assessments, with now ranking among the cleanest anywhere in the province of Ontario, a complete inversion of the district's mid-20th century reputation, achieved not through the land somehow healing itself passively over time, but through a specific, sustained, expensive combination of industrial emissions control and deliberate human land reclamation labor, measured now in tens of millions of dollars and tens of millions of trees. So did Sudbury's landscape recover, because nature is simply resilient given enough time. The way this kind of story often gets told in the softer, more comforting register. The evidence points toward a considerably less passive explanation. This land did not heal itself. It was healed, specifically and deliberately, by people who had first spent nearly a century actively damaging it. Once the same industry responsible for that damage finally faced enough regulatory and public pressure to change how it operated. The recovery is real, and it's genuinely remarkable by the standards of industrial land reclamation anywhere in the world. It is also not, in any meaningful sense, a story about nature bouncing back on its own.
It's worth being specific about how measurable this recovery actually is, because vague claims of improvement are easy to overstate in either direction. Comparative aerial and ground-level photographs of specific sites, the area around Coniston Hydro Road is one frequently cited example, taken across the span from the early 1980s through the late 2010s, show a transformation from visibly bare, blackened rock to substantial forest cover within a single human generation, a rate of visible recovery considerably faster than most naturally occurring forest succession would achieve on genuinely healthy, undamaged soil, let alone on ground that had spent decades as acidified bedrock. That speed is itself evidence of how much active intervention, rather than passive natural recovery, actually drove the transformation. Deliberately selected pioneer species, deliberately applied lime, and deliberately targeted planting locations chosen specifically to accelerate a process that undisturbed nature, left entirely to its own devices, would very plausibly have taken many centuries to achieve on its own, if it managed the acidified soil chemistry at all. Chapter 8. The city that still runs on the same ore. Whatever has changed about Sudbury's landscape above ground, it's worth being direct about what has not changed underneath it. This remains, in 2026, a city whose economy is still built substantially on exactly the same nickel-copper ore body Thomas Flanagan's crew stumbled across in 1883. Vale, the Brazilian mining conglomerate that acquired Inco in 2006, and Glencore, operating what were formerly Falconbridge's assets, continue running active underground mining, milling, smelting and refining operations across the Sudbury Basin today, employing thousands of workers directly and supporting thousands more jobs indirectly across the regional economy. Direct employment in mining and related extraction industries accounts for roughly 8% of Greater Sudbury's total labour force in recent data, a proportion that, while lower than the district's historical peak dependence on the industry, still represents billions of dollars in annual regional economic activity and tens of thousands of jobs when direct, indirect and induced employment are all counted together. This continuity is worth holding on to directly against the regreening story's more triumphant framing, because it complicates any version of this account that wants to end simply with trees and clean lakes. Sudbury did not recover by walking away from the industry that damaged it in the first place. It recovered while that same industry, under different corporate ownership and considerably tighter environmental regulation, kept right on operating in essentially the same location, extracting essentially the same ore, using processes that, while dramatically cleaner than open roast bed burning, still require ongoing, active management to prevent a return to anything resembling historical emission levels. The city's environmental recovery and its continued economic dependence on large-scale metal mining are not, in other words, two separate, sequential chapters of this story. They are the same chapter, running simultaneously, and the second one is the reason the first one required the specific, expensive, decades-long human intervention it actually got, rather than simply being left to resolve itself once the worst of the historical damage had already been done. So is modern Sudbury best understood as a city that solved its industrial pollution problem, or as a city that learned to manage the same fundamental industrial activity considerably more carefully than it once did, while still depending on that activity as heavily as ever? The historical and economic record both point toward the second description far more precisely than the first, which doesn't diminish what the Regreening Program actually achieved, but does mean the achievement was never about escaping the industry responsible for the original damage. It was about learning, the hard way, exactly how much damage that industry could do if left genuinely unregulated, and then building, over 4 decades, the most sustained corrective effort of its kind in the country, specifically because that lesson had already cost this landscape a century to learn. The 2006 acquisition of Inco by Vale is worth a brief mention on its own terms, because it marks a specific, symbolic transition in who actually controls the ground beneath this story. A company founded in Sudbury in 1902, whose corporate history runs in an unbroken line back to the earliest industrial exploitation of Flanagan's 1883 discovery, passed into the ownership of a mining conglomerate headquartered on an entirely different continent, meaning the same fundamental extraction economy that built and then very nearly destroyed this city is now managed at the corporate level by decision-makers considerably further removed from Sudbury itself than even the original 19th-century American entrepreneurs who first developed the Coppercliff operations. The mine names on the map, Froude, Stobie, Crichton, still honor the prospectors who staked these claims in the 1880s. The companies actually running the operations beneath those names today answer to shareholders and boardrooms thousands of kilometers away. Chapter 9. What Sudbury actually proved. Drive into modern Sudbury today along Highway 17, and the approach looks, for long stretches, like ordinary northern Ontario forest. Mixed hardwood and conifer stands, lakes that support fish populations again, a green landscape that gives very little visual indication of what this same ground looked like as recently as the 1970s. That transformation is genuinely remarkable, and by most measures used to judge industrial land reclamation anywhere in the world, Sudbury's Regreening Program stands among the most successful of its kind ever undertaken by a single city. The city itself has, in recent decades, leaned into this transformation as a specific point of civic identity and tourism messaging, in a way that mirrors, structurally if not in content, the same instinct that produced the moonscape myth in the first place. A complicated, difficult, true story compressed into a simpler, more marketable public narrative. Where the moonscape myth simplified a genuine impact geology story into the astronauts trained here because it looked like the moon, the modern regreening narrative can, in its more promotional versions, simplify a genuine 4-decade regulatory and reclamation effort into something closer to Sudbury cleaned itself up, without always foregrounding just how much of that recovery depended on sustained public spending, ongoing industrial regulation, and a specific, deliberate partnership between the city and the same mining companies responsible for the original damage. Neither simplification is exactly false. Both leave out the harder, more structurally important parts of the actual story in favor of the version that fits more easily into a single sentence. So let me answer plainly the question this whole account opened with, rather than let the current green landscape answer it for me. Did NASA send astronauts to Sudbury because the city's mining-ravaged terrain resembled the moon closely enough to serve as useful training ground? No. The astronauts came for the district's genuinely significant impact crater geology, a scientific asset created nearly 2 billion years before any human mining activity, and the resemblance between Sudbury's damaged landscape and the lunar surface was, for NASA's actual purposes, close to coincidental, however useful and durable that coincidence proved as a piece of popular mythology. Did Sudbury's landscape recover through some natural process of resilience once the worst of the industrial damage had passed? No. It recovered because a specific, sustained, expensive, 4-decade human intervention, combining industrial emissions reduction with tens of millions of dollars in deliberate soil treatment and tree planting, did the actual work that a century of unregulated open-air ore roasting had made necessary in the first place. The record was never actually hidden. It's in Michael Dentz's own repeated, specific corrections of the moonscape myth across decades of interviews. in the historical tonnage figures for sulfur dioxide released during the roast yard era, in a Regreening Program's own annual tree planting counts, in modern employment statistics that show mining still anchoring this city's economy today. What changed isn't the evidence. What changed is that a single, clean, visually striking anecdote, blackened wasteland, astronauts, the moon, traveled far better across 50 years of retelling than the considerably more accurate, considerably more complicated, true story. A meteorite that predates human history by nearly 2 billion years. An ore body that built and then very nearly destroyed a city. And a recovery that succeeded only because people spent 4 decades doing, by hand and by policy, what nature alone was never going to manage on its own. There is, fittingly, one more layer to this story's recurring collision between cosmic geology and human science, and it's unfolding today, 2 kilometers beneath the same streets this account has spent 9 chapters describing. In Vale's still operating Creighton mine, at a depth of roughly 2,000 meters, deep enough to require stacking 4 CN towers on top of one another to match, an international collaboration of physicists operates Snow Lab, the world's deepest clean-room science facility, built specifically to take advantage of the same rock overburden that makes Sudbury's ore deposit so valuable in the first place. That much rock overhead blocks cosmic ray interference almost completely, creating one of the quietest, most background radiation-free environments anywhere on the planet for detecting genuinely rare subatomic events. The predecessor facility, the Sudbury Neutrino Observatory, used that shielding to help resolve a decades-old puzzle in solar physics, confirming that neutrinos change type as they travel from the Sun, a discovery that earned the experiment's director, Arthur B. MacDonald, a share of the 2015 Nobel Prize in Physics. SNOLAB's current experiments continue searching for dark matter and studying neutrino behavior in the same depths where miners still extract nickel and copper from the same ancient impact structure that put the ore there to begin with. The meteorite that built this city's fortune poisoned its landscape and drew astronauts here by geological coincidence has now, in its own final twist, become the shield protecting some of the most sensitive physics experiments on Earth. Proof that this story's central irony, cosmic violence quietly underwriting human ambition in ways nobody involved originally intended, was never really finished. There's a final irony worth sitting with, because it draws together every thread this account has traced. The same impact structure that concentrated the nickel and copper into commercially valuable ore in the first place, the collision that built this city's entire economic reason for existing, is also, geologically, the exact feature that later made this landscape scientifically useful to a space program studying an entirely different celestial body. Sudbury's fortune and Sudbury's fame both trace back to the identical piece of underlying geology, arriving nearly a century apart for 2 purposes that had nothing to do with each other. The city spent most of the 20th century treating that geology purely as a resource to be extracted as quickly and cheaply as possible, with the resulting damage to the surface above it treated as an acceptable cost of doing business. It has spent the back half of that century, and the first quarter of this one, learning that the 2 questions, what's valuable underground and what happens to everything living above it, were never actually separable, no matter how convenient it once seemed to treat them that way.